few minutes till I get started, so welcome back. Hopefully everyone's having a good week with Halloween coming up and all of that. So, I don't know if you guys are the age, you're probably the age for Halloween parties and that type of stuff. I tend to avoid them, but to each their own. Hopefully you have something fun planned for the weekend. My neighbors keep doing these things where they drop candy off at the door. Have you guys ever heard of this before? Like, surprised they'd run up and drop candy off and run away. And it sounds like a great idea, except I have a 5-year-old and I'm trying to teach him not to take things from strangers. And he's like, ooh, a big thing of candy magically appeared. And I'm like, that kind of is a sense of danger associated with it. So I'm torn on what to do about it. I want to be polite to my neighbors because they're being super nice and stuff, but at the same time, I kind of want them to say, hey, we're the one that gave it to you, so I could actually give it to my kid without it being from a stranger. So those are the tribulations of my life. Before we get started today, is there any other questions about stuff? A few things on the radar. The next exam will be, I don't think it's next week, I think it's the week after that. And several people have asked about what is going to be on that exam, and we'll have to see. We'll have to see how far we get in chapter 5. It is going to start with chapter 4 though, so it'll cover chapter 4 and then however much we cover for chapter 5. If I was to guess right now, I believe that it's going to cover up to and including chemical reactions. So, and balancing chemical reactions. Now I know chemical reactions are not a fan favorite of the group in terms of actually doing them, but realize I'm going to make them super easy. Okay? There's not going to be any coefficients of like 11 or something like that in a balancing equation. They're going to be like 2s, 3s, things like that. So the exam is scheduled for November 10th. But I also want to make sure that you're aware, the Tuesday before that is election day, and because, yeah.
On the syllabus, it says it's 17.
Oh, really?
Yes.
Huh. Oh, that's a bummer. I might have to look into that then and see that. Okay, I'm going to look at it. The only problem with the 17 is if we have it on the 17th, I'm actually prepared and I got a calendar today.
Yeah, mine says the 10th.
Oh, I'm looking at something else.
Okay, great. Because if we had one on the 17th, we would have 2 classes and then another exam. And that would just be problematic. But I'm glad. Okay, good. So we have election day coming up, and then we have the exam right after it. So just be aware of that. Basically, that means we'll lecture through next week, see how far we get, and then once we do that, we can figure out exactly what's going to be on the exam. Okay? The other thing is the topic paper ideas. I don't really care how you get them to me. You can send me an email. You can just tell me after class, I want to do this topic. You can write it on a piece of paper and hand it in and so forth, and I'll take a look at it. The idea here is just to make sure that you're getting started on the right path and not choosing something completely crazy. I'm not sure what that would even be, but make sure you're not putting work in on something to find out that it's not a good topic later on. Again, I've never turned down a topic from anyone. The only thing I've ever done is like narrow them down a little bit so that you don't have super huge expectations to do it 3 to 6 pages. Okay, I think that's it in terms of things I need to say. Everyone else good? Kind of cold today? It's supposed to get colder. I don't know what the deal is with that. Then today is a clipping day, and I grabbed one, so I'm going to go ahead and go first because it just seems like that kind of day. but mine is about cruise ships. And the reason I chose it was over the last week I've heard 2 or 3 stories, or seen 2 or 3 stories about cruise ships and the fuel that they burn. So cruise ships normally burn a diesel fuel, and it has high sulfur content. So when sulfur gets into the air, it ends up forming H2SO4, and this is an acid. So it ends up forming an acid in the air and contributing largely to acid rain and pollutants and so forth. But what really caught my attention was the fact that first, they don't have any real restrictions on the amount of sulfur they can use. Like when you go to the gas station and you buy diesel fuel, it's always going to say low sulfur, right? Because it has a low sulfur content. The fuel has been specially treated to remove the sulfur. And cruise ships don't have that type of requirement. And the other thing is just the amount of fuel that they use. So one cruise ship, for example, called the Harmony, it's owned by Royal Caribbean, burns almost 1,400 gallons of fuel an hour when it's going through. So a car driving down the road at 30 miles per gallon, okay, let's say 2 gallons an hour. 2 gallons an hour, where one cruise ship is going to burn 1,400 gallons an hour. And then that's about 65,000 gallons a day when they're actually moving place to place and so forth. So this is just a huge, huge amount of gasoline that's being burned to move a cruise ship. And then at the same time, they're not using good gasoline in terms of the environmental concerns. So the stories I heard were about laws trying to be passed to make them burn low sulfur stuff. The cruise ships obviously don't want it because it costs more, but that's where we stand in terms of that. I was just amazed. 65,000 gallons a day. Think about how big of a fuel tank something would have to be out at sea for 4 or 5 days in those cruise ships. Now, granted, they're big ships. I don't know if you guys have ever seen a cruise ship or not, but it's enormous. It's like multiple buildings on the platform. Okay, so there's that. That's mine. Did anyone else find anything interesting? Oh, yeah.
That in your homes, the dust that collects on in your furniture and things like that has toxic chemicals in them.
Okay.
So yeah, it was talking about how certain plants are good for absorbing those toxic chemicals, so that so much won't collect on your furniture and
Okay.
things like that.
No, things you can do in your house to help with that. Absolutely. The only thing is, it's not very concentrated in terms of toxic. It's not like a ball of mercury sitting there or something like that. It's a relatively low percentage. But by all means, plants are helpful if you can keep them alive. Every time I buy a plant, it dies. They just don't like me. So I'll just clean, I guess. Anything else? Yeah.
So, bowling balls, right?
Oh, yeah.
Relatively low tech, hunk of urethane or whatever. I was at a bowling seminar, or product seminar a few weeks ago, because my dad owns a pro shop, so we're moving the bowling community. And this company is doing a brand new thing where they're coating the outside of their bowling balls in a non-Newtonian liquid, or non-Newtonian fluid, which is something that changes density when shock and pressure is applied to it. So there's they had the article I found was about scientists trying to understand non-Newtonian fluids because it's a relatively unknown kind of thing. Previously, scientists had thought that the fluid's properties, when it absorbs shock, are transferred to the edges of its container, which is not the case. It actually creates temporary, I don't know if it's bonds or what it is exactly, but the molecules don't compress the same way when quick pressure is applied to them. And the reason this is relevant to bowling ball technology is when you're trying to knock pins down, logic would say that you would want the heaviest ball that you can get your hands on because it will interact with the pins a certain way and have the most force. But with this stuff, since it hardens on impact, you can have a much lighter ball, which is easier for the bowler, and still have the same kind of impact with the pins. I thought that was really interesting, this high-tech stuff in a low-tech setting.
Well, bowling, I mean. we think of bowling, you said, it's low tech and stuff. The game hasn't changed all that much, but really, when you get into bowling, and granted this is not my thing by any means, but even like the way the lanes are coated and treated and things like that makes a big difference. I think, yeah. Non-Newtonian fluids are actually really, really cool. The most common one that you can actually make one yourself with cornstarch. And then as you hit it and stuff, it will change, resist puncturing and so forth. So there you go. Okay, anything else in the world? Okay, so we'll end it there. I know many of you don't like to speak up and so forth, or think you have interesting things. That's perfectly fine. I'm not here to pull teeth or anything like that. I just hope that in your individual searches of articles, you just find something interesting. Okay, so hopefully you can find something interesting out of it. It's not just a complete waste of time or anything. If nothing else, it's an easy way for you to get points in the course. So don't just blow it off either. Okay, so we're going to switch gears then, and we're going to start talking about the next chapter, chapter 5. Now, I put up here a subtitle for chapter 5, and I'm going to kill the lights here. Let's see if I can do this right. Okay. As chemical math. Now, I don't want you guys to get scared off by this, but at the same time, I want to come right out and say that in this chapter, we are going to be doing some math. And we need to do math so that we can keep track of what's going on in the world around us. So, for example, if I burn a forest, how much carbon dioxide is being produced? Well, in chemistry, we can figure that out. We have a certain amount of carbon contained within those trees, and then that carbon is released as carbon dioxide to the atmosphere. When you have a certain amount of acid rain that comes down on the ocean or a lake, how is that going to change the pH? Again, these are things we can figure out. Oftentimes, people look at models and so forth of very, very complex things and say that they don't have a mathematical basis for. They do, but we don't understand all the variables all the time. Those aren't the cases we're going to look at in this course. We're going to look at very simple, straightforward reactions where I've got a certain number of carbon atoms and I burn them to form carbon dioxide. How much carbon dioxide is produced? Okay? These types of things as we're going through it. And math is an important part of chemistry. Because you have to be able to measure what you're doing, right? With mass and so forth, we just keep track of everything that way. So I do think it's important to spend a little bit of time doing it. However, it's going to be simplified. Okay? The actual math that we do in here is not going to have, well, there's obviously no calculus, because I don't want to do calculus. I guess that's more obvious to me than you. Geometry, there's no geometry, no trigonometry, nothing like that. All of the math we do in here is algebra. Okay? And they break down to multiplication, division, and a little bit of addition, okay, for this chapter. So if you keep that in mind and don't panic about the math, I think we should be okay as we're going through the stuff. If, however, you are having issues, let me know, and we can take a look at it from the math point of view. So to start out with, we have to understand something about chemistry, and that is atoms and molecules are incredibly, incredibly small. We can't go and pick up one atom of carbon, move it next to an atom of oxygen, and have a reaction that occurs. They're just too small to do that with. So we do it with billions of these things at a time. So to keep track of how many different atoms, molecules, or eggs we have in a given situation, we're not counting individual ones, we're going to count groups of them. So in the picture here on the overhead, if I said how many eggs are there in these cartons, I would guess most of you would not start counting it as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and try and count your way through this. Okay? It's going to take a very long time to do that. We learn at an early age it's much easier to learn that there are 12 in each group, and then however many groups we have, we multiply that by one another to get the total number. Okay? So There are 12 eggs in each grouping there. If you count how many different dozens there are, let's see, 2, 4, 6, 8, 24 dozens. 12 times 24 is going to be 288 eggs. So very quickly I can figure out how many eggs are on this overhead without actually going through and counting individual ones. And you can do this with all different types of things. If I have 8 pairs of socks, how many socks do I have? 16. Okay? I'm blanking. Other ones. I don't know. I can't think of any other ones off the top of my head. But we have these words we associate with a number of items. Okay? And this is the same way with chemistry. Now, we're not going to count them with dozens by any means. We're going to use a much larger number. The other thing I want to show you about this slide is this is the math that we do. But in this class, we're going to go back and use unit analysis throughout this chapter. Okay? So to do this problem with unit analysis, what we're going to say is that we have 24 dozen eggs because there are 24 groupings up there. And 1 dozen eggs is equal to 12 single eggs. That's just our definition of a dozen. So throughout this chapter, we're going to learn different definitions that we can use to do these conversions. So this is then going to give us single eggs in the end. Okay, so dozen are going to cancel, single match, so we're doing great. And then it's a matter of doing the math. You remember this from our conversions we did at the beginning of the course? So 24 times 12 is 288 divided by 1 is going to be 288 single eggs. And that's how we would set up this idea of multiplying our dozens out using unit analysis. So chemistry, instead of a dozen, we use the term mole. A mole is just a number of things, just like a dozen. A dozen is 12. A pair is 2. A mole is 6.02 times 10 to the 23rd things. And you can have a mole of anything. The issue is it's a very, very large number. So if I was to draw this number out, this is the only time I'm going to draw it out because it's kind of annoying. 6 Okay. That's our number written out as a decimal. Now you can very quickly see why we use scientific notation to draw it out, because I don't think I could do it again without messing up. I hope I didn't mess up, but I think it's good. And that's because atoms and molecules are so incredibly small that it takes this many of them to get to a good amount to work with. A mole of carbon is, well, it almost fills a shot glass. Okay, if you have powdered carbon, graphite, when you're doing it. A mole of water is about the same as a shot. Okay, so if you had this many molecules of water, it would be roughly the same volume as a shot in a shot glass. So that's what we're talking about in terms of volumes and masses. A mole of carbon is 12 grams. So you can very easily measure out 12 grams on a balance, and you know you've got a mole of carbon. So just like a dozen, it is a number of things. You can have a mole of atoms, you can have a mole of baseballs. You can have a mole of bowling balls or of apples. It doesn't really matter what it is, it's just a certain number of them. Now granted, anything larger than an atom and so forth would very quickly be bigger than the Earth with a mole of them. But again, it's just a number of them. You guys, punch machines, where you used to feed the forms in and it punches the little holes out. Do you know what I'm talking about at all? Have you guys ever heard of hanging chad on elections, talking about elections? The little parts that hang on the bottom and then come off. Once upon a time, I saw a mold of those little things, those little punches, and it was about a bucket size of them, all in all, is how many that added up to be. So you can have a mole of anything, you just, once it becomes very large at all, it quickly, that large of a number overcomes things. Now, a mole is the fundamental central point for chemistry. And because of this, it is our mascot. And this is a picture of an actual mole. It's kind of scary looking, so we're going to ignore him and go with our friendly mole cartoon there. Okay. This is Avogadro the mole. He is our mascot for chemistry. He has a little sister named Millie Mole. And she's a little sister in Millie because Millie is small in the metric system. And Millie Mole is her name. Everyone likes Millie better. I should put a picture of Millie up. Let me see if I can find one really quick. Oh, there she is. There's a picture of Millie. Right there. And you know she's a good chemist because she's wearing her goggles. And safety first. So there you go. There's a little doctor version of Millie too with a stethoscope somewhere. But I don't see it on the first look. So there you go. Now, it's silly that we take the mole as a mascot, but it really shows how important a mole is to what we're doing. And throughout this chapter, and keeping track of the math of chemistry and those types of things, moles is the key part. To further prove this, Mole Day is National Chemistry Day in America, and National Chemistry Day is always October 23rd. Why October 23rd? Well, that's 10 to the 23rd. October is the 10th month, and so October 23rd is National Chemistry Day in the US. Chemists often get together at 6:02 because we're geeky like that, just to have the full 6:02 times 10 to the 23rd for breakfast. I don't get up that early though, so I don't partake in breakfast, but there are numerous chemists around here that do. But that's National Chemistry Day. Again, it's a silly thing, but it kind of underscores just how important the concept of a mole is. We could not do chemistry without the concept of a mole. It just wouldn't work in any way, shape, or form. So where did the idea of a mole come from? It came from Avogadro. Here is a picture of him. I think this could quite possibly be the worst picture in the world of someone. It's just a horrible portrait, but it's the only one you ever see of him. I've looked for better ones, and apparently none have survived. But he is credited with the idea of a mole. He said life would be much easier if we had some large number of atoms to move around instead of constantly trying to keep track of individual ones and so forth. Now, at the time when he was alive, we didn't have enough advancements in science to actually figure the number out, but he came up with the idea, and then later on we adjusted and found the actual number to match what he was talking about. That number happens to be 6.02 times 10 to the 23rd, and that's called Avogadro's number. And this is going to become a really important thing as we go through the chapter, because what it does is it allows us to work with large scales of things like 12 grams, 8 grams, things like that. Things we can actually measure and know how many atoms or molecules we have associated with it. So for this reason, Avogadro, which is also why it's the little mole is called Avogadro after him. Bless you. Now the main thing here is the definition that 1 mole is equal to 6.02 times 10 to the 23rd atoms or molecules. Okay, if you're talking about an element, it's going to be an atom. If you're talking about a compound, then it's going to be a molecule. And we can use that definition to answer questions that we may have about amounts. So, for example, how many moles of carbon are in 1 times 10 to the 14th atoms? So if I have 1 times 10 to the 14th, how many atoms, how many moles is that going to be? So to solve this, we're going to do what's called a moles to atoms conversion, or atoms to moles. It really doesn't matter. Anytime that you want to convert moles to either atoms or molecules, you're going to use Avogadro's number to do it. And to do this, we're going to set up, again, our unit analysis just like before. Use the relationship then to convert between them. So what's given to start with? 1 times 10 to the 14th atoms. And it's asking us to find the moles of carbon. So we want to convert atoms to moles, so we need a relationship between the two. Well, thankfully, we have Avogadro's relationship here, Avogadro's number. So over here, 1 mole goes on the top, and on the bottom goes 6.02 times 10 to the 23rd atoms. So we're using this definition then for our conversion there. Atoms will cancel. Moles will match. So grabbing my handy dandy calculator. One times 10 to the 14th times 1 is going to be the same, divided by 6.02 to the 23rd. I end up with 1.6 or 1.7 times 10 to the 10th. Wait, to the minus 10. The minus 10. So that's one type of conversion that we can very easily go through. Questions about that? So let's try one the other way. Let's say, how many atoms of nitrogen are in 7 moles of nitrogen? Okay. So if I have 7 moles of nitrogen, how many atoms of nitrogen am I going to have? Everyone have their ideas? So we're going to go through this exactly the same as before with the unit analysis. What's given to us to start with? 7 moles. And to be honest, this is exactly how we're going to do 99% of the problems in this class, especially in this chapter. So we're going to start with 7 moles of nitrogen. It wants us to find atoms of nitrogen. So we need a conversion between the two. Well, again, we're relating atoms and moles. So that's going to be Avogadro's number. 1 mole will go on the bottom. 6.02 times 10 to the 23rd, atoms on top. Mole cancels, atoms match. And then it's a matter of doing the math. 7 times 6.02 times 10 to the 23rd is going to be roughly 4.2 times 10 to the 24th. 4.2 times 10 to the 24th atoms of nitrogen.
So I have a question.
Yeah.
But on the first problem,
Mhm.
you got -10, but when I did, I got 36.
Okay. My guess is it's something about how you entered it. So, because 36 would be a really, really big one. So 1, I'll double check, to the 14th divided by 6.02 to the 23rd. Yeah, it's 1.7 times 10 to the minus 10. Okay. If you're still having issues, I'll walk you through it after class. Okay.
What did we say that answer to that one was?
This one, 4.2 times 10 to the 24th, or 42 times 10 to the 23rd. So now what you got? Yeah.
Okay, so for the 7 mole one, we multiply, right?
Yes.
And for that one, we divide it. How do you know when to do
Okay.
that?
So what you're always going to do is you're going to take this and the top number here and multiply those, and then divide by the bottom.
Okay.
And since it's 1, we can ignore that fact. Where over here, you have 1 times 10 to the 14th times 1, gives you the same, and then you're dividing. So I wouldn't necessarily try and remember, okay, if it's on the top, I'm going to multiply, bottom, divide. Just always do both of them, and then you'll come out okay.
Wait, I think he was saying why on that one you did 6.2, you're multiplying it, and then this one you divided it.
Okay? The reason for that is because here, we are starting with moles, so mole has to go on the bottom. And if mole goes in the bottom, atoms go on top. Okay. Where over here, we're starting with atoms, so atoms go on the bottom and then mole on the top. So right here in this problem, we've run across the 2 big issues that students have. Okay? First is just a thing of entering it in the calculator right. Okay? Don't blow that off. That's not something that's completely just sit down and do it. Practice with your calculator so you know that you can do it right. Also, a calculator would be very, very useful for this exam for obvious reasons, because a significant amount will be these types of things. The second thing is when we are using unit analysis, it allows us to check our setup so that we know when to divide and when to multiply and those types of things. Okay? So using unit analysis is actually very, very useful in terms of double checking things. And that's why, even to this day, I still use unit analysis when I do these problems, because more times than I like to admit, I would have them wrong if I was just trying to remember what do I multiply, what do I divide as we go through it. Okay, so let's do another one. Okay, so let's say how many molecules of H2O are in 0.25 moles of H2O. Let's say 30 seconds or so. Okay. Close enough. Okay, before I start working through this, any questions about this one? Yeah.
On the one, okay, like on the one that you just erased, you had it.
Yeah.
Well, I mean, there was on a bunch of them. It ended up being 4.2 times 10 to the 24th power.
Mm-hmm.
How are we getting the 24th power? Is it just the 1 mole adds to it? Because it was 23.
Yeah. So that one was. It was 7 moles. But then you multiplied it by 6.02 times 10 to the 23rd.
Mm-hmm.
So when you do that multiplication, you actually end up with 42.14 times 10 to the 23rd. But to make it proper scientific notation, this needs to be 1 in 10. So when you just moved it over 1,
Okay.
which then made it 4.2 times 10 to the 24th. If you answered that, 42 is perfectly fine too. It's the same number. But most calculators are going to correct for this and spit out that number, so I went with that, figuring that that would be what most people had.
Okay, I just didn't know how we got to it.
Yeah, but that's a good point. Either one of them is going to be perfectly fine. I mean, if you wanted to, you could do any number that means that number, you're good. Okay, so here we are then, figuring out our molecules for water. Here we have molecules because it's a compound, but that doesn't change anything else. What's given to start with is 0.25 moles. And it wants us to find molecules. So I see the word molecules, so my first thought is going to be Avogadro's number. And 1 mole is equal to 6.02 times 10 to the 23rd molecules. Mole cancels, molecule match. So I'm doing good there. And then I'm dividing these 1.25. Okay, so 0.25 times 6.02 to the 23rd. 0.25 times 6.02 to the 23rd is going to be 1.5. Yeah. 1.5 times 10 to the 23rd. 10 to the 23rd. Okay. So again, that's 0.25 times 6.02 times 10 to the 23rd divided by 1 is going to give me 1.5 times 10 to the 23rd. Everyone agree with that? When I was doing this lecture yesterday, I made like 9 mistakes in class. They just thought I was randomly making up numbers by the end. I don't know what I was doing. Okay, so that is how we're going to convert between moles and atoms and molecules, or vice versa. That allows us to keep track of how many actual atoms there are in any given reaction. Right? Yeah.
Well, we have question where after we get that, then we're gonna have the part B or part C, where we have to take the answer and then,
We will. I'm not going to jump into that yet because we're going to build up to it a little bit. My plan is not to have anything more than 2 steps. So you would do this, and then you would do one more out of it. In the past, I've done more, so you may see some sneak in from time to time. But my goal is to kind of simplify it this year and only have like 2 steps. In chemistry itself, you could actually have 4 or 5 steps as you march through the various things, but there's really not a whole lot of use to doing that besides just trying to make it difficult. Okay, so any last minute questions between converting moles to atoms? Great, and it's nice to be able to keep track of how many atoms we have so that we can see what's actually going on in our reactions, but that's not how we measure things in real life. So the way that we measure things in real life is normally based on mass. I've got a balance and I pour out some of my reactant and I see the mass of it. So to understand mass, we have to learn a second conversion that's called molar mass. Molar mass just simply means the mass of 1 mole of something. Now, for elements, this is really, really easy as long as you remember where it is. On the periodic table, the number under your symbol is your molar mass in grams. So carbon's molar mass is 12.011. I'm just going to round it to 12. Selenium is 78.96, 79. So the molar mass is just the number on the periodic table underneath a given element. And we can use this in exactly the same way that we did with our other conversion. We're just going to change what's in the brackets. This time, instead of saying 1 mole is equal to 6.02 times 10 to the 23rd, that's Avogadro's numbers conversion. The relationship we use here is 1 mole is equal to the molar mass. So a question could be, how many grams of sodium are in 3 moles? So if I want to do a reaction with 3 moles of sodium, what mass would I need on my balance to have that amount? So let's go ahead and let's walk through this one together, and then we'll do a couple examples. So going through the steps, same as always, what's given to start with? 3 moles of sodium, and it wants me to find grams of sodium. So I need a relationship between moles and grams. Whenever you have moles and grams and the conversion between those, that's always going to be your molar mass. So we know that 1 mole of sodium, we go to the periodic table, number 11 is sodium, so the mass is 23, is going to be 23 grams of sodium. Moles are going to cancel, grams match. So then doing the math, 3 times 23 is going to be 69. Divided by 1 is the same number. So it would take 69 grams of sodium to have 3 moles. 69 grams of sodium.
So you just round the number up?
Yeah, just round it to the nearest number. I'm not real particular about it. It just makes life easier, and I can kind of do it in my head at the board, so
Okay.
you guys can do the same. So this is our second conversion then, and it's a mole of something is equal to the mass of it. Let's have you guys try one. Let's say how many moles of carbon are in 100 grams. So on your paper, see if you can figure out how many moles of carbon you would have if you have 100 grams of it. Okay, let's say 15 seconds or so. Okay. So again, going through the same steps, 100 grams is given to us to start with. And we want to find moles of carbon. So we need a conversion between the two. Well, this time, is moles going to go on the bottom or on the top?
Top.
On the top. 1 mole is going to go on the top because that's the unit you want. 12 grams of carbon goes on the bottom. Grams cancel, moles match. And then it's a matter of doing the math. 100 times 1 is 100. Divided by 12, I end up with 8.3. 8.3. Yeah.
Was the whole purpose of doing the unit analysis to prepare us for
Largely.
introducing, to make it familiar, so it's not?
It helps with conversions, but since you're multiplying by 10, they're not really all that difficult. This is more of the payoff for it. Yep. Because even in this part right here, many times you can reason out that you need to divide, and that makes sense. But when we go on to the next steps in stoichiometry and so forth, you can't always just reason out in your head. That's not something that students can generally do, so it pays off a lot there. Yeah?
I'm sorry, you probably
No,
said
it's okay.
what the process was, but where do you get that 12 from?
Okay, so the 12 comes from the fact that we have carbon on the periodic table. It's the number right under it. So under the carbon, it's 12. So you can use whatever element it is, just look right under it, and you can see the given mass of it. All right. So this works really well and easily for given elements. Okay, elements, we can just go to the periodic table and look. Doesn't matter what. Bromine, Br, is 80. Calcium is 40, and so forth and so on. But what about if it's not an element? If you've got something like water? Well, in that case, water is H2O. So 1 mole of water is equal to 1 mole of oxygen plus 2 moles of hydrogen, because we have 2 hydrogens and 1 oxygen each. Well, now we're back to the elements. So we know 1 mole of oxygen is 16 from the periodic table. 1 mole of hydrogen is 1, but we're going to multiply that by 2 because there are 2 of them to give us a grand total of 18 grams per mole. So when we have compounds, you just add up the components. So oxygen has a mass of 16. Hydrogen has a mass of 1, but we have 2 of them, so we're multiplying it by 2. 16 plus 2 then gives us 18.
Oh, so we're just taking the mass of them.
Yep.
Okay.
The mass of each of them, and then accounting for the number that you've got in your compound.
Okay.
Yeah.
So that's the atomic mass, correct?
Yes.
So it's like just the same thing, molar mass
Yep.
and atomic.
Yeah. The only technically the only difference is atomic mass is in AMUs is the unit, where the molar mass is in grams, but no one ever worries about that. Yeah?
Is the 2 times 1 is the 2 from the H2O?
Yep.
So
Mhm.
if that's like, I don't know. Like,
27.
it'll be 27. right?
Yep.
Okay.
Mm-hmm. Yeah, and we'll do an example of that in a minute. Yeah, actually, this is why it took so long to figure out the number for moles and why 6.02 times 10 to the 23rd is. The reason why that's Avogadro's number is because that's the number of atoms it takes to equal the mass on the periodic table. It's not just some random number made up. That is the number of atoms it takes to get to a mass of 12 for carbon, or a mass of 4 for helium, and so forth. And that's where it all comes from in the end. Okay, so let's try, have you guys try one? Let's do NaOH. See if you can figure out how many grams 1 mole of NaOH would be. Okay, everyone got their ideas? Okay, so here we're going to add up the various components. Sodium, if we look at the periodic table, is 23, plus 16 for the oxygen, plus 1 for the hydrogen, is going to give us 40 grams per mole.
And this is how you calculate the molar mass.
Exactly, yes.
Mole.
Mhm.
Okay.
So this would be how much mass of that material it takes to be equal to 1 mole.
Okay.
Now, I have on the one you did above, this 16.
Mm-hmm.
So you took the hydrogen and the oxygen and added them together?
Mm-hmm.
So you didn't round the oxygen, you just kept it out at 15?
Well, oxygen is 15.999,
Mhm.
so I rounded it to 16.
Okay, so then the 2 times 1 is the hydrogen?
Yes.
Okay.
Mm-hmm. And let's try one like that. Let's say AlOH3.
Do the same thing we just did.
Yep. What would the mass of 1 mole of aluminum hydroxide be?
I'm sorry, can you tell what AL?
Oh, Al is number 13.
Sorry.
No, of course, once you ask, you're going to find it. That's just the way it works. It's my favorite element, by the way, on the periodic table, in case anyone cares. Okay, let's say 30 seconds or so. Everyone got their ideas? Okay, so to start out with, just for formality, this 3 means we have 3 OHs. So rewriting this, it's going to be as if we have 3 OHs there. Okay. So adding it up, AL is 27. OH is going to be 16 plus 1. So each OH is going to be 17. And we've got 3 of them. So multiplying that out is going to be 51. 51. So adding 51 and 27, 78 grams per mole. 78 grams per mole, yeah.
So you just added the mass of O and H together? So you just did 16 plus 17, 16 plus 1, you just did 17?
Yep.
But could you have did like 26 plus 16 times 3?
Plus 3 plus times 3?
1 times 3?
Yep. Mm-hmm.
Okay.
Yeah, you should get the same number, right?
Yeah,
I don't
certainly.
like it.
Oh, okay. Yeah, no, it'll come out the same.
Okay.
Yep. Yep. So 70, and you might be slightly off if you round one way versus the other. This one wasn't particularly difficult to get the rounding, but sometimes it's like in the middle. I'll be fine with that. It's not a problem. Everyone good with that then? The aluminum hydroxide? Yeah.
What if the 3 was the negative? Would that ever happen?
No. No, because
Your charge or.
you can't have like negative presence, like you would list it. So yeah, you won't ever see a case like that. Okay, so let's continue on with aluminum hydroxide then, and say how many moles of aluminum hydroxide are in 64 grams. So how many moles of aluminum hydroxide would we have if we have 64 grams of it?
Is aluminum hydroxide always going to be AlOH3?
Yes. The reason why it is because hydroxide is the OH. It's an ionic compound, so you don't use prefixes. So to balance out the charges, it would have to be AlOH3. Okay, so to work this one out, we're going to start with our 64 grams of aluminum hydroxide. And we want to find moles of aluminum hydroxide. So converting between grams and moles is always our molar mass. So 1 mole is going to be equal to 78 grams. Grams will cancel, moles match. So 64 times 1 is 64 times divided by 78 is going to be 0.8. Yeah, 0.82. 0.82 moles. 0.82 moles. Is that what you all got? Yeah. So doing this mathematically you're multiplying and you're dividing. I think you can all do that on your calculators. That's not what trips students up when they're working through all these types of problems. What trips them up is the actually setting them up and so forth. So there's good practice. It's good to practice this a little bit and set these types of problems up as you're going through. I'm not ending for the day, but it kind of sounds like. So just make sure you go through and practice setting these things up. Okay? As we're gonna do. Questions about these?
And right now, that's about as far as we would go for a test question.
For a test question, there would be one more step. I can actually show you one here. Yeah, we got time. So mole, as I said, is super, super important to chemistry. That's silly for me to say that. It doesn't describe nearly how important it is. So we can sit here and we can take a number of grams we measure out, and just physically measuring with a balance, and from that we can find a number of moles. But once we're in moles, we can actually go to a whole wide array of things. There's probably 20 different units and 20 different systems we can go to with different values. We're not going to just do all of that, but what we are going to do is we're going to go from moles to a number of atoms or molecules. So going from grams to moles is going to be the molar mass. And going from moles to atoms and molecules is our Avogadro's number conversion. So we can put these together and answer questions such as this. How many atoms are in 100 grams of carbon? So how many atoms are in 100 grams of carbon? Well, first and foremost, I don't know a relationship between grams and atoms. There isn't one. So whenever anything is given to you that's not in moles, the answer, the first step that you want to do is convert to moles. Okay? So if it's something not in moles, convert to moles. I always make the joke that if you don't know what to do, convert to moles. If you're copying off your neighbor, you're hoping they're converting to moles. It's always the answer is converting to moles. Anytime something's not given to you in moles, it's never wrong to convert to moles. So we're going to go from grams to moles using our molar mass. And then once we're in moles, we can then go to atoms using Avogadro's number. So this is going to be two steps. The first step is the molar mass conversion. The second step is Avogadro's number conversion. Do you guys want to give it a try, or do you want me to do it on the board first? Have an opinion? Okay, on the board, sounds great. So we're going to start with 100 grams of carbon, and we want to get to moles of carbon. So grams to moles is going to be our molar mass. And for every 12 grams, it's equal to 1 mole. So grams are going to cancel. Moles match. 100 times 1 is still 100 divided by 12. Is going to be 8.3. So in 100 grams of carbon, I have 8.3 moles. But that's not what the question is asking me for. It's asking me for atoms. So I'm going to use that to get the atoms of carbon. You guys see how this is the same thing over and over and over again. Something I'm starting with, something I'm ending with, the relationship between the two. I want a big stamp so I can just put them up here and not have to draw them all out. Okay, so I start with 8 moles of carbon. I'm going to atoms, so that's going to be my Avogadro's number, and say 1 mole of carbon is equal to 6.02 times 10 to the 23rd atoms. And doing the math, 8.3 times 6.02 to the 23rd is going to be 4.99, so let's just say 5 times 10 to the 24th atoms. So if I went and I massed out 100 grams of carbon, then that would contain 5 times 10 to the 24th atoms of carbon. And this is important. Say, for example, I'm burning wood from a forest or for heat or whatever. Wood is mostly made up of carbon. So if I burned 100 grams of it, that would mean 5 times 10 to the 24th atoms of carbon are being released in the environment. Okay? And then whatever happens to them after that. They would actually turn it into carbon dioxide in that case. But that's how you would go about doing a two-step problem. First one being a conversion that we know, the second one being a conversion we know, but we got to put them together. Questions there? Yeah.
When I did the first conversion,
Yeah.
I went 8.33.
Okay.
And then I got 5.01 in the end.
Yep.
Okay.
Oh yeah, absolutely. Yep, not a problem at all. Again, the main thing for me personally, it's not the number. Like, you guys all are fully aware that I don't care that you understand that's 5 times 10 to the 24th. That's not the point of this. It's the thought process behind it, where you understand these relationships and then setting them up together. So yeah, you're all in good shape there. Yeah, and that actually goes in terms of partial credit and so forth. If you're setting up a problem, especially on the fill-ins where I can see your work, and you've set it up, but then you hit something on your calculator wrong or something like that, you're still going to get most of the points for it because you've gone through the process of setting it up and so on. Good there? Yeah.
So when you said there's like a million different ways, like 23, 20,
Yeah.
you could just literally keep doing this analysis and keep breaking it down to other.
Yeah, once you get to moles, from moles you could go to products of a reaction, you could go to concentration in the solution, you could go to a volume of a gas, you could go to pressure, you could go to different things along those lines that all come out of the mole. So, for example, if I had a map here and these are my two conversions, there would just be all different arrows going out, and every arrow would have a different relationship associated with it. And that's why moles are so important, because it allows us to understand what's going on. Because once you're in moles, you can basically go anywhere you want.